Okay, good morning. Today is August 11. We're going to go on with the explanation on the response, primary response of the shift structure, right, as a whole beam. And remember, chapter 2 dealt with shear stresses in bending. And since this is a beam, which is not that long, in this case, we need to consider shear stresses in the hull. So we are going to review a video of that. And also, in the case of the hull, we have to include longitudinal bulkheads. That means that the relations that we obtain in chapter 2 are not enough, okay, to calculate these cases. So we have to explain something extra in order to be able to solve this shear stress problem in hull beams, okay? Also, in the assignment, I posted one problem which is related to an example. That example will be described shortly, and the PDF of that example I posted in the Aula Virtual in the module number 5. Okay, module number 5. There is a PDF file in there, so please download it. Okay, so all of that for today's session. Okay. Can you confirm me that you see my full screen?
Yes, doctor.
Okay, thank you. So this is what we studied the last session. We said that we could consider this as a method to analyze the response of the hull beam in waves. Okay, it's what we call a quasi-static equilibrium situation, right? So we impose an equivalent wave, okay, on the ship, and we assume that in this situation we are in a quasi-static equilibrium. So that means that this force and that force has to be equal, and they have to be aligned. Okay, if the ship had a very large trim, then we should worry about LCG and LCB, right? Because the inclining will make the LCB and LCG not being equal, right? But we're going to assume that we have small trims, so LCG equal to LCB plus W equal to the displacement are going to be the conditions that we have to look for to have static equilibrium, okay? Now, so this is to have summation of forces equal to 0. This is to have summation of moment is equal to 0. Okay, so this is the displacement times LCB. This is the displacement. They have to be equal to the W and also the product of the W times LCG. Once we have this, all of these, we are in equilibrium. It's a quasi-static equilibrium. That's chapter 1. So we make a cut here. Remember, these are the new sign convention for shear force and bending moment. These two are positive here. This is, of course, a negative phase. So we integrate from minus L over 2 until X. Right? Now, in this end and in this end, the shear force and bending moment are 0 because it's free end. Okay, and you see that there is no support. There's no specific point of support. That gives us a problem, but we'll see that in a second. So dv at dx is equal to minus, and we can integrate, and this is the result. So we can integrate from here, minus L over 2 until x, or we can integrate from x until L over 2. We need this negative sign, because if we integrate from minus L over 2 until here, so it's going to be v at L minus L over 2 minus v at x. And that's why we need this negative here, because I have v positive in this case. Okay, so we can do this integration at any cut that we need, and we can determine the distribution of v of x. And then we can get the other equation. Let me insist on this, okay, that this is, okay, this is positive. This is negative. That's because the new sign convention that we are using, because we try to follow the ship classification societies. Okay. Now, after we have determined the distribution of shear force, we do integration similar to integration to that, and we go from here to here, and we can integrate this like this. Okay. In some cases, specifically for this one here, okay, W of X has a very strange distribution, right? Because, for example, you have a bulkhead, right? So between bulkheads, you have a large weight, for example, because of the cargo. And then in the next compartment, there is nothing. So there is a change, a sudden change in the weight distribution curve. So these integrations are a kind of long to develop. So yeah, what we can do is we can numerically integrate, but we have to use a very small delta x in order to have a good approximation. Okay. Now, let's suppose that somebody is interested in the Hall deflection. Okay. The problem with this is that there is no geometric boundary conditions. Okay, you cannot establish one point along the length where you know that deflection is a certain value. No. That means that we cannot evaluate the two constants of integration if we try to evaluate the whole deflection. I'm sorry, we have to live with that. So we have the whole, like this one here, like this. So we have here something like that. And let's suppose that this is the bending moment. Okay. But we have already calculated this. For example, let's suppose that I have here 0, I have 0 here, and let's suppose that we have something like this. It's equal to the Young modulus, the sectional inertia. Remember, in this case, we assume that this is a beam, but with variable inertia. And then we have W, comma, XX. Remember, in the vertical direction, we call it Z, so we call it W, the deflection in the vertical direction. Remember, U, it's in the X, V, Y, W in the vertical direction. Okay? And the problem is that if we integrate these twice, this should be W. Okay? If we do that, then we will have these two constants. But there are no conditions, geometric boundary conditions. So there are no geometric boundary conditions. Determine C and D. Okay. So this is what people usually do. Okay. we assume, so commonly, this results as the two ends at no deflection. Okay, it's as simple as that. It's just an assumption. Okay, so we have a beam here. We have an integration. What we do is we assume that W at 0 is 0, and we assume that W at L is 0. I'm sorry, this is L over 2. This is minus L over 2. Jesus. Okay, with these two conditions, we could evaluate D and C. Okay, that's all what we can do. Now, that means that usually what we do or what we apply this result is not because of absolute values, right? Because we know that the deflection at the two ends is different than 0, right? But it's just a way to present results. But we can use these results if we want to see, for example, the influence of the Hall deflection. See, you have a Hall, right? And because of the action of the weights and the buoyancy, this deflects. If you have the shaft here, right? If the Hall deflects a lot, they will make the shaft to deflect too. But that will generate extra loading on the supports of the shafting. Okay. For example, if you have the engine room, right, it could deflect a lot, and that will try to impose extra loading on the foundation of the engine. So if you want to see if that makes some sense, yeah, you can evaluate the deflection curve of the hull, right? And imagine that this deflection of the hull are imposed on the position of the supports of the shafting, and that generates changes in alignment. And there were some problems with very large ships. Okay, they deform a lot the hull, and as a result of that, they had problems with the alignment. So the reduction gears suffer some damages because of this, right? The hull deforms, and because of this deformation, the points of support, okay, or the bearings of the shafting system, they move a lot. And because of these motions, the reactions on the supports change a good amount. And because of that, they suffer some damages in the reduction gears, or even in the there was some breakage of the shaft. Okay, and you can use that using this deflection curve from the hull. But remember that this is you don't see absolute values. What you try to see is the relative values, right? For example, if you see that you have the engine room here, okay, you see that this point moves one amount, a different amount, and a different amount. And what you could try to see if this is not a straight line, right? That means that it imposes some bending. And that, of course, changes the points where you have the supports of the shafting. And that takes to the problem that I just described. Okay, so this is the way some people sometimes do this, they present these results if you are interested in deflection. Okay, otherwise, if you are interested in shear force, bending moment, you have to, if you're applying this method, what you do is just impose the wave change, the draft, and the trem. And once you have an equilibrium, you start applying the section method. So you make cuts along the length of the ship, you integrate the loading, and you get shear force. You integrate the shear force and get the bending moment. Once you have shear force and bending moment, you can proceed to calculate shear stress and normal stress. Okay, that's the procedure. We're following the second procedure that we presented. Remember, the first one is to do a full dynamic response of the shipping waves, which is very long. The second one is this one, which we impose an equivalent wave, and we assume that a quasi-static equilibrium. And the third one, which is very simple, is just apply the formulation from the Classification Society. I'm going to present just in a couple of comments in a few seconds. Okay, so that's that. Now, this is the example that I was mentioning. This is the example that you have to complete for your assignment. Okay, let's suppose that we have a box barge. Okay, that means that it's a box. Okay, so the block coefficient is 1, section coefficient is 1, prismatic coefficient is 1. So it's just bang, bang, bang. Okay, now we have the weight of the hull. There is some cargo from here to here. In the aft, let's suppose that we have a superstructure and we have some machinery, and this is uniformly distributed in this area. And then at the end, there is a castle, forward castle, waiting this, but it is a jump here. There's some empty space here. Okay, so this is the ship that we want to analyze. Okay, so remember, this is in this case, since the section is rectangular, okay, the area is going to be equal to B, which is constant, times the draft. This is the draft. So in this case, the section is simple. Okay, so this is the draft as function of X. So B times T, that's your area, because this is a rectangular section, because this is a box barge. Okay, then we integrate in X. Oh man, and yeah, I'm integrating just the volume. That's why I put the specific weight on the left-hand side. Okay, so this is one equation because we know the total weight, which is the summation of all of that. Also, we need to determine the angle of trim. Okay, the angle of trim, in this case, I'm calling alpha. Okay, you see here, this is a trim angle. Okay, and this is mean draft. Okay, so mean draft is measured here. There. Okay, and again, if I multiply the force per unit length times the arm, which is X, that produces the combination of the volume times LCB, right? And that has to be equal to this. Okay, so we have to calculate the total weight, we have to calculate the LCG, and with these two equations, we should be able to calculate mean draft and alpha, the trim angle. Now, this is the case for a box barge. If you had a ship, in that case, what you have to do is you have to iterate, because the integration cannot be developed, because the beam or the sectional area changes along the length of the ship and also with the draft. So what you have to do is you have to assume values for T and alpha. Okay? Take the values from the hydrostatics for the distribution of area for that mean draft for that alpha. Superimposing you see that there is a wave here, and then do these two calculations. If these two equalities are correct, that means that you have assumed correctly the mean draft and trim. Otherwise, you have to iterate. If you have too much displacement, what you have to do is you reduce the mean draft. If the LCB is larger than LCD, then you have to increase or decrease the alpha. That's why the computer is so useful. Now, we can determine total weight. We can determine LCG. Please, some people, you have to be certain that you are able to calculate LCG, okay, from the distribution of weights with no error. In this case, it's typical. We have the LCG aft. That's why we see the negative sign here. So with these two values, we put it into here and here. We solve these two equations and we can calculate mean draft and alpha. That we said last session that equivalent wave height, use it 1.1 square root of L. So what you have to do is you take 100 meters, convert that into feet, plug it into here, and the result is going to be in feet. Transform to meters, that's going to be height. And then divide it by 2 to get this value, which is the amplitude. Okay, so this is wave equivalent wave amplitude. It's equivalent height. So the height is twice the amplitude. Okay, so if you do that, you have to calculate these two parameters. I'm not going to give it to you, so you have to calculate it. Let's suppose that you have found it. Okay, now we have to proceed to integrate for the shear force and bending moment. Okay, now after you have done that, see here, all of this is T times CB, this is area. So you take area times gamma, and that's buoyancy force, including the wave. Okay, and here you have the weighting, the weight, pointing downwards, obviously. Okay, so after that, we apply this equation, that's the equilibrium equation. Remember this negative sign, we're using the convention from the classification societies. So you integrate this, and this is the result. Okay, so let's suppose that I integrate from here until here. Okay. In this case, for example, we can assume that the loading follows a step type distribution. That's typical because of the influence of the weight. Okay, the weight is constant in a certain area, then changes. Okay, now, yeah, you can say that the loading, the buoyancy distribution changes continuously. Yeah, but But you can do two integrations, but yeah, that once is enough. So what we can do is we can say, okay, P of X is very small, change is very small from here to here. That's what we do. So if that's correct, that means that the integration of this is just P times delta X, and that's what we're saying here. Okay. Now, after developing this calculation, you can plot the distribution of the shear force. But the distribution of the shear force will give you something like this. And instead of having this, we are going to have something with inclination and probably some curvature. But if delta X is small, we can assume that the curvature we can neglect it. So dm dx is equal to that. Please, this is negative, this is positive, and we can proceed to the integration. Now, the integration of this line, okay, we can apply a trapezoidal rule. So we say this is the average in height, this and that divided by 2 times delta x. That's that. Okay? And in this case, this is the result. Okay? So this is the ship, and this is my loading. Please, this is force per unit length. Okay? And you see here that I just put these rectangles, but these rectangles is each one of these. So it goes from here to here. So it's like this, like that, 0, and then goes to positive, etc. So the area, how much has to be the area below this curve? See, I have this, let me see. We can draw this, something like this. So on. The area, the total area, has to be equal to what and why? Anybody? The total area below this, the loading, has to be equal to what? Anybody?
In 0.
Why?
Because we're in equilibrium.
Exactly. So in P, you have minus W plus buoyancy. If you integrate both, you're going to have total weight, total buoyancy, and they have to be equal. So the total, so we integrate from minus L over 2 until L over 2, that will give you 0. And yeah, you integrate from here to there, the result is going to be the shear force at the end. Shear force at the end is going to be 0. So yeah, correct. And then this is the result. So I have these values. So this is in the center. This is the value of x at the center of each interval. So the intervals are 5 meter long. Okay. Remember, minus L over 2 is minus 50. So this is just in the middle of the interval. That's what I'm writing here. I plus 1/2. Okay. So this is the loading, okay, in this interval. And that's minus 50 until minus 45. And with this, I can integrate, I can apply these two relations, and we can integrate and do something like this. Okay. In the case of the shear force, you see that it is the integration gives us some good values. In the case of the bending moment, this value should be 0. Now, we don't get 0, we get 15.6. But if we compare that with the maximum value, which is 22,000, okay? So this is 1,000 of that. So it's very small, okay? people, you can either proceed this following this method, and you could try to apply a different integration procedure, whatever. But it's always a good idea to face these problems. Okay, it's something very common in Shear structure. And these are the results. Okay, so this is the loading that we had before, and if we integrate, we get something like that. Okay, so in here, I have the loading is negative, so the shear force is positive. Okay, and you see that this area positive and this area is negative, and more or less they look about the same. And it has to be like that. Why? Because when you integrate this, the result up to here has to be 0. That corresponds to the bending moment at the end. Okay, and that will give us very interesting things. Okay, so if this area is equal to that, that means that you integrate from here to here and you have a large integration. That's this value. And then you change sign. So you start decreasing, the integration start decreasing until you close it to 0. Okay, so immediately we see that a couple of things here. No, okay, this area and this area are the same. So if you integrate from here to here, this is max for the around midship. But in here, okay, it's typical. You start at 0 and you have to change sign, because when you integrate, this area has to be equal to that, right? That means that in between half, that's L/4, usually you have large value for shear force. Okay, so every time we are worried about shear force, in the case of the hull, usually we look towards minus L/4 plus L/4. Every time we're looking for bending moment, we look at midship. That's because of these results. Comments, people? Any comments? Comments? People, any comment?
Doctor, but at the end, the moment it isn't 0.
Yeah, that's because the integration gives us some problems. But you see that the result, even though it's not 0, is very small. And this is a plot of the previous table. See, this plot is just corresponds to this table. And this value is 15.6 is the value that you are seeing here. But proportionally, it's very small. What you could do is you can try, for example, use this integration with a more efficient scheme of integration. Right? For example, you could try to use, what you could do is you can integrate separately the weight curve and the buoyancy curve, because the weight curve follows this step-like distribution, and the buoyancy changes continuously. What you can do is you can integrate the weight function. You can integrate it using this simple sum, but the variation of the buoyancy, you can integrate it using trapezoidal rule. And the result is the shear force. And the result of the shear force, what you can do is you can integrate it following, for example, a Simpson rule, which is more efficient. Sure, the result will be, you will close this curve in a better way. But still, I mean, you tell me here, what you see in here. Do you think this curve basically closes? Because this value here, even though it's not 0, is 1,000 times smaller than this one. So that's it. Any other question, people? No? Okay. So we have said a couple of words about, mostly about the second method, which is an equivalent wave, a quasi-static equilibrium. And if you choose correctly the equivalent wave height, okay, the results are going to be acceptable, right? That's basically the concept. The third method to evaluate this shear force and bending moment acting on the hull is just to apply a classification rule. That's what we call the third method, okay? So for example, I'm using here the DNV rules from 2015 for ships with length less than 100 meters. And this is the result. This is the formulation, okay? So they give you a formula for S sub 0. This is for, the S stands for still water, and the 0 stands for at the midship. Okay, so you apply this value, length and beam in meters, and the result you will get in kilonewtons meters. Okay, and then this value here is valid in this region around midship. Okay, so this is 0.4 of the length. Okay, and then from this point you draw a straight line until the aft and forward perpendiculars, and this is the approximation that the classification rule give you for the still water bending moment distribution. Okay, this is very important. The third power to the cube. That means that when you have a small ship, length is small, raised to the third power, the result is going to be very small. So that's why, remember, last session I mentioned, and I said that this problem, this hull bending problem, primary hull bending problem, it's a problem of small ships. When you have, I'm sorry, for large ships. When you have small ships, this bending moment and shear forces are just, they don't produce important effects. The stresses that they produce are very, very small. Okay? If you go close to, for example, 80, 90, 100 meter long, in that case, yes. In that case, this is a very important problem. Why? Because you have the length to the third power in the case of still water. In the case of the waves, it's going to be power to the second, raised to the second power. People, questions about this? No? People, you have to be careful because here, the signs are very important. Okay? Remember, positive sign means that the ship is, the hull is smiling or is sad. Positive. Anybody? According to the convention,
Sad.
it's sad. Yeah, it's sad. So you have to be careful with that. That means that you are like that. That's okay. Now, for the responding waves, okay? Similarly, they give you two formulas, this and that. That stands for waves, and that stands for 0. That's about here. You have one value for sagging and one value for hogging. But remember, these two produce bending moment with different sign. So when you combine still water and waves, right, you have to be careful. Because in one case you add, and in the other case you subtract. Okay. Now for small ships, like this is the formulation I'm applying, this is not much of a difference. In your case, in your homework, you have to apply rules for ships with larger length. Okay, and in that case, yes, you have to be careful because these expressions come with the sign, because that tells you the idea that in larger ships, this problem is very important, really. Okay, so again, we depend on the length to the square, and this CW, okay, that's, if I would have to say something, I would say that CW is more or less proportional to the wave height, equivalent wave height. More or less, that's the idea. Okay. So according to the length of the ship, you can expect a larger wave to apply. Now, the thing is this, more or less, okay? If you have a ship, a small ship, well, don't write on my screen, please. Like this, okay? If I have a wave in the order of the length, okay, that will produce a large response of the structure. So you're going to have something like this. The problem is that in this wave, about this is the length, okay? You're going to have height, okay? If you consider a larger wave, okay, for example, like this, okay, and you see that I have larger height than this one here. But the problem is that since the wave is longer, right, the effect on the structure is reduced. Okay, that's why this CW goes with the length of the ship. Okay, so you have a larger ship, longer ship. That means that the longer wave will produce a larger effect, bending effect. And a longer wave will have probably a larger, and that's why CW, you will see in the rule that depends on the length of the ship. Now, once you have calculated MW0, okay, you have to do something similar to the distribution of the still water bending moment, okay? So these values, you apply them in this area. And then from this point until the aft end and this point to the forward end, we just join with the straight lines. Okay, so this is an approximation of the distribution of bending moment in still water and in waves, following the classification rules. Don't believe me, you will have to your opportunity to see this in your assignment. Okay. Okay. This is an example that it's not a large ship. It's a 42-meter long ship. It was part of the design that was developed by Engineer Moreno. Did this 20 years ago, and I had this information, so I put it from his thesis. He's right now he's the Lloyd's surveyor for this area, Panama, Peru, and in Ecuador, I think. So he has improved in his professional career. Okay, so we have this distribution. Okay, and we prepared this weight distribution. Okay, so we consider these items, the weight of the hull, superstructure, fresh water, diesel, and the machinery. Look at the hull distribution. Okay, this is tons per meter, so this is force per unit length. And you see that increases, this is constant, and then decreases. This is a model, right? The distribution of the weight along the length of the ship, it's more complex. But this is a way that people can do in order to simplify. Okay, so it's like straight, constant, straight. It's a way to approximate the distribution of the weight per unit length of the hull. The superstructure from here to here, we assume it as uniform. Fresh water, we have one tank about here and another tank down here. Still, we have two tanks in here and about here, so we see that we have some part and some parts. The machinery is in here, so we have these three steps. Then we add to the right. So we have for each one of these intervals, we have this weight per unit length. In this case, we consider this, we should include more partitions. We should include 20 partitions is a good number. Okay, that's that. And then what we do is we multiply this times delta X times X. So we're able to calculate LCG. So we have total weight and we have LCG. Okay, that's typical of this type of calculations. So this is the distribution of the weight. So this is these numbers. But here I added each one of the components. So you see the hull, it changes like that, then it's constant, and then start reducing. We have diesel here and here, machinery in the central part, 2 fresh water here and here, and the rest is substructure. It's a small amount. You see that it's like has the typical follow of the weight distribution, which is like a stairs. We did just integrate. Okay, this is the ship lines. So you have an idea how they look like. And then we integrated. So here, I have the weight distribution. So this value, these values, we have it as dots here in blue. So it's like this, etc. The other curves are continuous, and those are the buoyancy. Okay, this is for still water. So in the central part here, this magenta, this is distribution. In the central part, in the midship area, you have a larger buoyancy because the section is higher, it's larger. So you have more draft, more beam. And then in the case of hogging, okay, you have a crest in the midship area. So that means that the buoyancy in this part increases, right? And then here, see, you're gonna have a throw in this area. So probably the aft end of the ship is out of the water, and you see that there's no buoyancy. Similarly in the forward end, okay? When you apply in the sagging condition, you have a crest here, a crest here. And that's why you see an increment and an increment. So you see that in the case of hogging, there's going to be some positive bending moment. In the case of sagging, you're going to have a negative bending moment. In what case do you have the deck in compression, people, before we go to the break? In what case are you going to have the deck in compression? Mr. Tenemea, please. In what case, hugging or sagging, are you going to have the deck in compression? Mr. Tenemea, please.
Yes, doctor. I think in sagging condition.
Sagging? Mr. Cedeño, Axel Cedeño, what do you say? In what condition are you going to have the deck in compression? Hugging or sagging?
I would say hugging, doctor.
Hugging? No, in sagging. In sagging, you are like that. Deck will be in compression. In sagging, hugging will be like that. In that case, the bottom will be in compression. These things are very important because we have to check the possibility of buckling, right? So you have to check that. Okay. So if you are like this, that means that the deck will be in compression. So you have to use the sagging bending moment to evaluate the compressive stress. And that compressive stress, you have to check it against the critical stress of the plating. So you can be sure that there is no buckling in your deck plates. Okay, let's spend a couple of seconds here before we have to take a break. And here, okay, in blue, we have the bending moment, okay, from the effective wave, and in red from DMV. So this is like method 2, this is like method 3. This is for still water. And here, you have to be careful because this thing here is still water plus waves. Okay? And here, directly, when you integrate, you have the two effects together. So let me repeat that. Okay? When you apply the like that. In waves, you have the two effects combined. So here, the blue line is the result of the integration in this condition. So you have together the effect of the wave plus the effect of the still water. So if you want to compare, what you have to do is you have to calculate, let me go back. You have to combine these two curves in order to compare. That's what you see here. There is some small, it's not a single paralleloid. You have some changes in curvature here. Because the region where you expect the maximum bending moment in still water and in waves is a little bit different. Okay, so the red here is the combination of the two, and the result of simple the integration. This is for the hugging condition. And we see that it's very close. Means that in general, we can expect that if we apply either one would be nice. Now, if we apply the equivalent wave, yes, it's make more physics, right? Instead of just applying a rule. It's like a black box. You get the length, you got the CB, you got a beam, and bang, you get a bending moment. So it's, for me, it's better if I do the integration and I check the results. So it's always a good idea to try to do both. You have to do both in your homework. Questions, people? Questions?
Doctor,
Yeah.
the case of the weight, the region of the weight is added to the still water in the DMB
Yeah.
rule.
Yeah. Yeah. In the case of the equivalent, the blue curve, you have both effects combined.
But the points
separate them.
are different. I could see that the points are different in the DMB rules. At point 10 is more higher.
I mean, you cannot expect to follow exactly this distribution. I mean, this is a very simple distribution. It's typical, but the maximum values are very close.
Okay.
Remember, please, that neither are precise. If you need more precision, come to ship dynamics. Do the full dynamical response, and then do something like this. So do cuts, integrate in time, and then plot against the length of the ship. We did this with who? Oh yeah, some years ago. Published some of these results for a 120-meter long local tanker. It was very close, really. So, but it was very interesting that we see the three methods working together. Also, this was also investigated by Miss Priscilla Salazar. She just started her PhD in Belgium this past year. We did this some 10 years ago. And we did this in irregular C. So it was a random calculation. Very interesting. Okay, people, let's take a break here. And when we return, we'll go back with our agenda, okay? Please, Andy, you can